We'll start this video off with question N. We are going to decompose a very complicated logarithm into simple logarithms, single logarithms. And the first thing we notice when we do that is that this is a quotient. We're taking the common logarithm of a quotient. A numerator here, a denominator there, and that means that when we apply the quotient rule, we'll be taking the logarithm of the numerator minus the logarithm of the denominator. Now, there's no parentheses around this product, but that's because all these terms are tied together by the multiplication, and the parentheses are not necessary here. This term, on the other hand, is squared separately from the 4, so we need parentheses here. After using the quotient rule to break this into two logarithms, we then turn our attention to the first one and see that this is yet another product of three expressions. So 5 times x squared, so that's log base 10 of 5, plus common log base 10 of x squared, plus common log base 10 of the cube root of the quantity x plus 1. So that's the first logarithm in the difference here, decomposed somewhat. Now this logarithm is a product as well, so logarithm base 10 of 4 and a logarithm of the quantity x plus 1 squared. So we decompose that using the product rule, but I put another set of parentheses, brackets in this case, around that group because that subtraction applies to the entire logarithm here. So that's why this is inside another set of parentheses. Now going back to the head of the equation, log of 5 is not going to be changed at all. That's as simple as you can get that logarithm. But we use the power rule to bring this exponent around front of this logarithm, and so that becomes 2 log x. That's as simple as that one is going to get. Then the cube root we write as this quantity raised to the 1/3. Here we distribute, and continuing on, we distribute the negative to the log of 4 and the log of the quantity x plus 1 squared, and I went ahead in one step and brought the 2 around front using the power rule. I brought the 2 around front here, so this is negative log 4 minus 2 log x plus 1. And then there's no change in the last grouping here, except that I used the power rule to bring the 1/3 around the front of this logarithm. And now this is as much as we could possibly break this logarithm down, and so that's the end of that question. Okay, question O then is an equation that can be turned into a quadratic with a substitution. Anytime you have a variable raised to a power that is double the other variable, that to which the other variable is raised, you can make an appropriate substitution that will give you a quadratic. So in this case, I've let x cubed equal u, because I know that x to the 6th is the same thing as x cubed squared, and so if x cubed is u, then x cubed squared, or x to the 6th, is u squared. So I substitute that in, and I have u squared minus 26u minus 27, which is easily factorable. The factors are u plus 1 and u minus 27. Then I substitute back the x cubed for that u. So this is x cubed plus 1. Subtract 1 from both sides. X cubed is equal to negative 1. And then if you take the cube root of both sides, the cube root of x cubed is x. The cube root of negative 1 is negative 1, because negative 1 cubed is negative 1. Then, for the other factor, I substitute x cubed back in for the u here. So x cubed minus 27 equals 0. Add 27 to both sides then, and the cube root of both sides here gives us x is equal to 3. So these are our two possible solutions, negative 1 and 3. So then I substitute them back in to check. Negative 1 to the 6th, since it's an even power, is just positive 1. Negative 1 cubed, on the other hand, is negative 1, as we just discussed. And so negative 26 times negative 1 is positive 26. And then we subtract 27, and that does give us 0, as in this original equation. Now, 3 to the 6th is 729. I don't know about you, but I needed my calculator for that. And 26 times 3 cubed, which is 27, is 702. There's a negative in front of that, so this is 729 minus 702, which is positive 27. And then at the end of the equation, we're subtracting 27, so once again that gives us 0. So both of these solutions check. All right, now in question P, all we're really doing is calculating the decay factor and substituting in a time value to find out an amount after a certain time. Well, anytime you are calculating the decay factor, you're going to work with the half-life. So the half-life of carbon-14 is given here as 5,730 years. That's approximate. You'll find slightly different approximations in different from different sources, but that's what we're using here. So the amount after 5,730 years is half, and we have a 1 here, an invisible 1 before the e, and so there's the time t, and there's the unknown decay factor k. So you take the natural log of both sides here, and you have natural log of 0.5 is equal to 5,730k, because these are inverse operations and they cancel one another out. And then you divide both sides of the equation by 5,730 by 5,730, and you have natural log of 0.5 divided by 5,730, and in this case that comes out to approximately negative 0.000121. And we didn't have the 1 in class. Someone else came up with 122, and that was because probably because of the slightly different half-life that was given. But that's what we're looking for in this question, is the decay factor. Then we are told that there is this is the amount, this is the number of nanograms of carbon-14 in some sample of some sort, and it is where we want to know how much is going to be left in 9,079 years. So that's the amount in the A of t equals a sub 0 times e raised to the kt. That is that's the number of years that we're evaluating the function a of t. And so we substitute that in here for the time. We just found out the factor k, and when you run all that through your calculator, you get about 0.500027. These digits are not very significant, especially since we're talking about nanograms, and so that's roughly 1/2 of a nanogram.